All right, let's take a look at the warm-up here. Let's find the eigenvalues and eigenvectors for this little matrix A. So a little practice from yesterday. We'll start off, step one is to find the eigenvalues by using this determinant equation, taking the determinant of A minus lambda I, and asking when is that thing equal to 0. So first we'll calculate this determinant thing. Now when we calculate this determinant thing, we're going to get something called the characteristic equation. That's the name of the polynomial that we're going to get from the calculation of this determinant. So we have 2 minus lambda, 1, 1, and 2 minus lambda. All that A minus lambda I really does is subtract lambdas on the diagonal. Calculate the determinant. Looks like I have 2 minus lambda times 2 minus lambda minus 1. I'm going to expand out that product. Looks like I will get 4 minus 2 lambda, so minus 4 lambda plus lambda squared minus 1. I'm going to simplify that and kind of reorganize it. Lambda squared minus 4 lambda plus 3. I'm going to try to factor it. When I factor it, looks like I can get lambda minus 3 and lambda minus 1. That's my characteristic equation, and the question is, when is that thing equal to 0? When is our determinant equal to 0? In this case, I can see it's when lambda equals 3 or lambda equals 1. All right, any questions about the eigenvalues? I found the eigenvalues. For the eigenvalues, now we have to find the eigenvectors. So I'll start with lambda equals 1. So when lambda equals 1, and I have to plug this thing back into my homogeneous system here, and I'm plugging in lambda equals 1. Those A minus lambda I is essentially this thing. It's just lambda, subtracting lambdas on the diagonals. So all I'm really doing is plugging in lambda equals 1 to that thing. We get the matrix that looks like 1, 1, 1, 1. Of course, I could write that as augmented with 0, but I don't really have to, because the row operations aren't going to affect those zeros on the right. I see that these two rows are multiples. Does that surprise me at all? Why is that not a surprise? In fact, I would be surprised if they weren't somehow multiples in this case.
Because they're
Dependent, absolutely. If they were independent, there would only be one solution to this system. If there's only one solution, it would have to be the trivial solution. It would have to be x equals 0. And x equals 0 is not an eigenvector. So I'm looking for eigenvectors. I expect there to be independent or infinitely many solutions. I expect there to be free variables. All right, so I can simplify this to 1, 1, 0, 0. And we're going to need that assumption that they're multiples later on as we go into 5.5. But for now, we'll just say it makes sense. Simplifies to this. Once it's in this nice reduced form, I can write out the equations. So I can get x1 plus x2 equals 0. And x2 is my free variable. I'll write out my solution here. It's a vector with an x1 component, x2 component. But x1 is just equal to negative x2. And x2 is just my free variable. I factor out my parameter. I'll get a vector that looks like negative 1, 1. So I'll say that's my eigenvector, negative 1, 1. But of course, we know that any multiple of that is also an eigenvector. That's done with the first one. Any questions about that first one? So in this case, the associated eigenvector is negative 1, 1. There are fractions in there. I would want to multiply it by something to get rid of the fractions, just to make it a little cleaner. I'll go on to the next one. When lambda equals 3, well, now I'm just plugging in lambda equals 3 into my A minus lambda I. So I have 2 minus 3, which is negative 1, times 1, 1, and 2 minus 3, which is negative 1 again. There's my new matrix. It's this thing times x equals 0, solving for x. Once again, I'm really just row reducing here. I could take the second row and add the first row to it. Of course, I'll get zeros here. Not surprised by that. Has to be that way if I want infinitely many solutions. My equations here look like negative x1 plus x2 equals 0. And x2 is, again, my free variable. If I wanted, I could have multiplied through by negative 1, put in root form. In fact, let's just do that. It'd be multiply through that by negative 1, I would get this. The same thing as getting this. My solution in this case, x1 is equal to x2. x2 is my free variable. This thing looks like x2 times 1, 1. So to summarize, lambda equals 1 gives me an eigenvector of negative 1, 1. And lambda equals 3 gives me an eigenvector of 1, 1. Any questions about that? Make sure if you have questions about any of those steps, please ask. Please stop and say, what's that thing doing there? You can just assume right now this will definitely be on the exam. Basic eigenvalue calculation. Now you have to show all these steps, but at the same time, most of your calculators should be able to do this as well. So please check your steps. Right, most of the 89s, I think even maybe the 86s and below should be able to do eigenvalues, eigenvectors. Mathematic, I can of course do it as well. There's our matrix. I just store it as A. And there's lots of things I can do here. I can say, give me the eigenvalues of A. There they are, 3, 1. I could say, give me the eigenvectors of A. There they are, 1, 1 and negative 1, 1, just like we calculated. Or I can say, give me the eigen system of A. That will give me a list of the eigenvalues and their associated eigenvectors. So just start typing in eigen, and you'll have a whole list of commands here. It's not just fun to say eigen. Okay. The only other German I know is weiter. Weiter, weiter. And I'm pretty sure that's wrong, and I'm pretty sure I only know that because it was in Die Hard. So. All right. Any questions about eigenvalues, eigenvectors? Okay. All right, this is the same plan for attack we had yesterday. We pretty much got through what are they. They satisfy this thing. It was lambda x. That's kind of their definition here. We basically have a matrix where we times it by this vector, and the result is just scaling that vector. We figured out how to calculate them. First, we can find the eigenvalues using this equation. And then we take those lambdas and plug them into this equation to solve for our eigenvectors. Oops, this one was actually 0, and this other one was 0 vector. And once again, I think it's important to see the thought process how we generated these two. We took this one, our definition, just a little algebra to get to here. Right? We said, okay, this can't be invertible, because if it's invertible, all I get is the trivial solution. If this is not invertible, then it's determined it has to be equal to 0. And that gave us a second equation. Those are the equations we used. But now we know how to calculate these things. The question is why, right? What are the properties? What are the relationships? What's important about eigenvalues and eigenvectors? We're going to talk about the properties, relate them to our old ideas of invertibility. We'll also talk about similarity transforms, similar matrices, and how we kind of generate these things. All right. Properties. List of 3 properties. The first one is incomplete here. The eigenvalues of a triangular matrix are what? Let's think about it here. Here's A. 1, 0, 0. Let's put a value up here even. 3. What are the eigenvalues for this matrix? If we calculate them, we have to go like this. But that's triangular. So it's easy for me to calculate the determinant of this thing. What is the determinant of this thing? What is the determinant of this thing? Well, the determinant here is just the product of diagonals. Right? So we're not quite there yet. But it's just 1 minus lambda times 3 minus lambda. And so when is this thing equal to 0? When lambda equals, not everybody all at once. 1 and 3, thank you. All right, there we go. And so, of course, if we look back to the original matrix, what's special about 1 and 3? Just our diagonal entries. Right, and that's not surprising. We can kind of look at that and say, oh, yeah, that's going to happen every time. Right, because as soon as we generate this thing, calculate the determinant, it's just going to be the product of the diagonals. That's just a product of a bunch of 1 minus lambda, 3 minus lambda, 10 minus lambda, 6 minus lambda, whatever those diagonal entries are. And if it's just those products, without plus or minus a bunch of extra junk, remember it's that extra junk that kind of messes things up. Right? It's having this thing plus 3 that makes us do work to find out when this thing is equal to 0. If it's just this product of stuff, then it's easy to find out when it's equal to 0. Okay. So the eigenvalues of a triangular matrix are just the diagonal entries. Diagonal entries. Right? The values on the diagonal. All right, so that's going to be useful, right? We're going to want to grab those values. We're going to pull them out right away when we get them. The next thing, A is invertible if and only if 0 is not an eigenvalue. And this is one we can throw into our giant inverse matrix theory. Right? I think we were on what, like Q or something way down there. Now we have another one. When is a matrix invertible? Only if 0 is not an eigenvalue. That's kind of a weird one, right? Let's think about that one. Well, we have our starting equation for eigenvalues and eigenvectors. So we can kind of look at that and say, well, what happens if 0 is an eigenvalue? What happens if 0 is an eigenvalue? On the right-hand side would be equal to 0, so we would have this thing. Okay, and 0 actually can be an eigenvalue. It can't be an eigenvector, but it can be an eigenvalue. But if it is an eigenvalue, we get this thing. So how come this prevents A from being invertible? I mean, if 0 is an eigenvalue, we get to this. That tells us if 0 is an eigenvalue, this can't be invertible. So here we have 0 as an eigenvalue. Why is this thing not invertible now? Why is A not invertible here? Invertible because if it is invertible, what would happen? If it is invertible, then there's only the trivial solution, which means that x is 0. If x can't be 0, because that can't be an eigenvector, if x is 0, then this whole thing is not true, right? Because we said, look at this thing for eigenvector, eigenvalue. These are paired up. So it says that if this is an eigenvalue, if 0 is an eigenvalue, then the eigenvector would have to be 0. Well, that can't be true. So therefore, this thing can't be invertible. Makes sense? So it's a little thought proof there, a thought justification. The big idea is one more thing for our matrix invertibility theorem. It's invertible if and only if 0 is not an eigenvalue. And the last one, eigenvectors from distinct eigenvalues are linearly independent. Eigenvectors from distinct eigenvalues are linearly independent. And that's going to be a useful result. It's going to help us justify some steps that we want to do later. So if we look up here, just maybe foreshadow what that might mean. Here we had a 2 by 2 matrix. And as we were working through this, we were getting eigenvectors. Our eigenvectors are two-dimensional vectors. Here's one and here's one. Now we have a 2 by 2, so we're going to have two eigenvalues, or eigenvalues here. Means we're going to have two eigenvectors. And because our eigenvectors came from different eigenvalues, because they came from two distinct eigenvalues, that last little property says these two eigenvectors are going to be linearly independent. Well, that's kind of a good thing. If we have two eigenvectors in R2, and we know they're linearly independent, then these eigenvectors are going to span R2. That's going to be a useful result for us later. So we're going to use that idea of linearly independence to tell us whether it's a span or not, whether they form a basis for R2. All right, so right now we'll just kind of take that last property and tuck it away, and we're going to use it a little bit here. Any questions about our big properties? All right, there's going to be a lot of results from class today, kind of a lot of talking, sorry. Tomorrow's going to be a work day. We're getting a little bit ahead of the schedule, so now we have tomorrow is a full day to pound out a worksheet, have a quiz, kind of really do some good work to make sure that we're soaking in all the knowledge that we're getting. All right, similar matrices and diagonalization. A is similar to B. Here's our definition for similar matrices. A is similar to B if there exists some matrix P where A is equal to P inverse B P. Or P A P inverse equals B. That seems so random. Well, if that's true, then the nice thing about A and B is that they have the same eigenvalues. That's the big important property for similar matrices. And we have to be kind of careful here. It says similar matrices have the same eigenvalues. But that doesn't actually work in reverse here. We could have plenty of matrices that have the same eigenvalues that are not similar. We can't find that other matrix. But it just says similar matrices have the same eigenvalues. All right, so instead of just kind of giving us a bunch of random stuff here, let's think about why similar matrices. Why could this be a useful thing? We've talked about an idea like this before here. So if we think about how we, I'll say recall, that to find the solutions to linear systems, what did we do? Here's my system. 1, 2, 3, 4, augmented with 2 and 3. I had that system. What did I do to that system to find the solutions? I row reduced it. I did some sort of row operations to get it to some nice form. Like this. Well, the reason I did that, the reason I did that row reduction is because row operations didn't change the solutions. So I could take this system, do a bunch of stuff to it, and say, okay, when I'm done, when I transformed it over here to this reduced form, the solutions are still the same. And that's really what I have going on here. I have a matrix here, and I'm doing some matrix here, I'm doing some stuff to it, and the result is going to be some different matrix, maybe an easier matrix to work with, but I know the eigenvalues are going to be the same. So I've done some work to it, but I've preserved the eigenvalues. Okay, so just like here, I've done some work to this system, but I've preserved the solutions. Now it's important that we have some new process for doing that, because it turns out our old process of row reduction, that will change the eigenvalues. All right, so we can't just row reduce some nice form and say, oh, all right, eigenvalues 1 and 1, woohoo. Otherwise, pretty much all of our matrices would have eigenvalues of 1 and 0. Row reduce things to 1s on diagonals. Okay? So row reduction will change the eigenvalues. It doesn't change the solutions, but it'll change the eigenvalues. But the similarity transform, where we multiply both sides here, one by matrix, one by the inverse, that will not change the eigenvalues. Okay. So that's a similarity transform. Now it turns out that given some A, sometimes we can find this transformation, find some P and D such that A equals P times D, P inverse, but D is a very special matrix. It's a diagonal matrix. And that would be great, right? Because a diagonal matrix has to have the same eigenvalues as this thing. So that means this has to have eigenvalues right on the diagonal. So I look at the diagonal matrix and say, what are the eigenvalues? Oh, it's just the product of diagonal entries, right? So if this was, they have to have the same eigenvalues. So that's what it's got to be. So because it's a similarity transform, the eigenvalues of A and D have to be the same, but D is diagonal, so the eigenvalues have to be those diagonal entries. Now the question is, what's P? What's the magical P that makes this transformation possible? That it takes this A and it transforms it into a diagonal matrix. Well, it turns out P is a matrix whose columns are eigenvectors. So this is going to be a big idea of how we're going to use these eigenvalues, eigenvectors. Once I take A and I can find out the eigenvectors and eigenvalues, it's a process of diagonalizing A. I've taken A and done this transformation to get a diagonal matrix D. All right, so that's probably a little cloudy right now. This is the main equation here, how we diagonalize. A is equal to P times D times P inverse, where P is a matrix that has the eigenvectors as columns, and D is a diagonal matrix that has eigenvalues on the diagonals. So, this is what we did in the warm-up. Warm-up, we had our matrix A, we had our two eigenvalues, and we have our two eigenvectors. And so what that means is that if we take and say let P equal and D equal these two matrices, we should be able to do this diagonalization. So I'm going to let D equal 3, 0, 0, 1. I'm putting my eigenvalues on the diagonals. By convention, I'm going to put the biggest one first. I should probably switch these numberings around here. Call that 1 and 1, and this 2 and 2. So I'll put the biggest eigenvalue first and then go down the diagonal like that. So then my P should be, well, the eigenvector associated with the eigenvalue of 3 is 1, 1. And the eigenvector associated with lambda equals 1 is negative 1, 1. So there's my P. All I have to do is calculate P inverse. Go ahead and calculate P inverse. Give me a break from talking. What's P inverse? It was, wasn't it? Yes, thank you. All right, how's that for an inverse? Look good? All right, and so what this tells me is that A, 2, 1, 1, 2 should be equal to 1, negative 1, 1, 1, 3, 0, 0, 1, and 1 half, 1 half, negative 1 half, 1 half. We should do that product and should get the result. Of course, I'm going to cheat here. And along the process, we'll see little things we can do in mathematics here. So that eigensystem gave me the eigenvalues and eigenvectors. It returns them first as a list of eigenvalues and then as a list of eigenvectors. What I'm going to do when I run this is I'm actually going to store it as two lists. I'll say values and vectors, for instance. Now I'll have a list of values and val, and I'll have a list of vectors and vec. I'll go like that. I want to see what the values are, there are the values. I want to see what the vectors are, there are the vectors. So those vectors should kind of be like my P. There's only one problem. If I look at this in matrix form, is that what I want my P to be? What's wrong with it? Yeah, that's right. So when they give me that list of eigenvectors, they're just giving me a list of the eigenvectors. But when I talk about matrices in Mathematica, it's giving me a list of the rows, not a list of columns. So I got to transpose that to make it right. So really my matrix P that I want should be the transpose here. That's what I want P to be. Now actually I can't define things when I have matrix form. It kind of messes up the notation. So I'll redefine that like this. And I can look at it in matrix form. So that's my vector P. My vector D, I want to be a diagonal matrix where the eigenvalues are on the diagonal. Actually, Mathematica has kind of a way for me to do that because it's a diagonal matrix. And all you have to do is put in a list of the diagonal entries. So when I do this thing, that's what I'll get. So this thing is that diagonal matrix. I'll hide that. I'll hide that. And then I'm going to do the product. P times D times the inverse of P. And I want this whole thing to look pretty. Hooray! So we got back to where we started from. All right, so just an example of we create that matrix P to be a matrix whose columns are the eigenvectors. We have this diagonal matrix D, which has the eigenvalues of the diagonal entries. That's the diagonalization of P. Any questions about that? In some sense, it's almost like a factorization. We said if we had the matrix A, we could break it down to the products of L and U. And that was nice because we took a difficult matrix and made it into an upper and lower triangular matrix. Well, this is kind of nice too because we're really breaking it down to a product of three nice matrices. There's a lot of special properties about P and P inverse that we're going to see maybe later. But D is really the most powerful thing here, that it's just a diagonal matrix. All right, any questions about that? All right, well now there's a little question here. We just can construct P, no problem. We take eigenvectors, we throw them in there, but we did construct an inverse for P. And we just kind of assumed that one was going to exist, and we were able to find it, so that worked out well. Is that always going to be the case? How do we know that there was going to exist a P inverse thing here? I didn't question it in the last problem. I just started constructing it because in the last problem up here, I knew for sure there was going to be an inverse for P. Why? Absolutely. I had two distinct eigenvalues. I have 1, lambda 2. Therefore, I was going to have two independent eigenvectors. So 2 by 2. I have independent columns. It's going to be invertible. Okay? So if I have an n by n with linearly independent columns, I know it's invertible. So that fact that these eigenvectors from distinct eigenvalues are independent told me I could find P inverse. So then the question is, when would this not work? This was a 2 by 2, as opposed to a general n by n. And I had two distinct eigenvalues. Therefore, I knew I was going to get two independent eigenvectors. But what if I had a 10 by 10? Am I guaranteed to get 10 distinct eigenvalues? Not necessarily. So the problem is going to come up with if we don't have all distinct eigenvalues. Turns out we can get a lot of different results when we look at this determinant thing. When we go to find the eigenvalues, we're going to end up with a polynomial. We did a 2 by 2. We got a quadratic. Yesterday we did a 3 by 3. We could have expanded it to get a cubic. In general, for an n by n, we're going to get an nth degree polynomial. So here's a result that I maybe could get from a specific matrix. I could do this calculation for some large matrix and get a result that looks like this. And the question is, when is this thing equal to 0? So when is this equal to 0? When lambda equals a whole bunch of values to guess from here. When lambda equals 1, 2, 3, 3, 3, 3, 3. When is this thing equal to 0? Square root of negative 1, so plus or minus I. All right, so we have a very special theorem in algebra. Fundamental theorem of algebra says that if we have a nth degree polynomial, there are n roots to that thing. Not necessarily n real roots, but there are n roots. They can be real roots, they can be complex roots, but there are n of them. So here we have the three different results we can get for lambda. We can get nice, distinct values, a 1 and a 2. We can get repeated values. I have 5 factors of this factor here. And that means that technically I have all the roots I need. They're just 3, 3, 3, 3, 3. So these ones are repeated. Distinct roots, repeated roots, complex roots. We're going to have to find out eigenvectors for all these different cases. Now the distinct roots are great because when I plug in lambda equals 1 to this thing, I will get an eigenvector. There it is. When I plug in lambda equals 2, I will get an eigenvector. I will get 1 eigenvector. Not 2, I will get 1. The problem is what happens when I plug in lambda equals 3. I'd like to get 5. Sometimes I'll get 5. Sometimes I won't get 5. I have to get 1, but that's all I'm guaranteed is I'll get 1. I could get 1, I could get 2, I could get 3, I could get 5. That's going to be a problem. Right, if I can't get 5 distinct 5 independent eigenvectors, when I plug in lambda equals 3, I'm not going to have enough eigenvectors. I'm not going to have enough linearly independent vectors to form my matrix P to do the diagonalization. That's going to be a problem. Now when I go over here to my complex values, these are really 2 roots. It's plus I minus I. Those are both distinct. So this will give me 2 eigenvectors. So this will be fine. The question really is these repeated roots. How am I going to handle these things? So the question is, do I have enough eigenvectors to find my P? Right, to form this matrix. Or another way we can think about this, maybe more formally, can I find a basis for Rn of eigenvectors? So let's look at an example. What are my eigenvalues here? 1, 1, and 2. I plug in lambda equals 1 into a minus lambda I which is 1 minus lambda 2, 3, 0, 1 minus lambda 4, 0, 0, 2 minus lambda. I'm going to plug in lambda equals 1. I want to see how many eigenvectors I get. So go ahead and do that. Plug in lambda equals 1. Find the eigenvectors here.
Minus lambda I, such a
All right, I plugged in lambda equals 1. Now what? Now I'm going to row reduce the best I can. Kind of weird here. I don't have a 0 or a 1 in the first column, but I don't. So now what I'm going to do is I'm going to go divide this first one by 2 maybe. Like this. That's wonderful. So I have my pivot position here. And now I'm going to do a whole bunch of things. I could divide this by 4. I would turn this into a 1. And I could use this 1 to eliminate this 1. And because this is a homogeneous system, and I don't have to worry about messing up values over here, I'm going to be a little sloppy about this, because nothing's really going to change. I'm going to turn this into a 1. I'm going to take this 1 minus that 1. What am I going to get here? 0. I'm going to use this 1 to eliminate this 1. Is it going to change this value? Nope. I'm going to take this 1 and eliminate that 1. That one's going to turn into a 0. So really a lot of this stuff when dealing with a homogeneous equation, I don't have to really worry about the actual steps. I know what's going to happen. And I'm going to get this as a result. What does that tell me my eigenvector is? Well, it tells me that x1 is a free variable. x2 is equal to 0. x3 is equal to 0. So I get this thing. And I'm sad. I'm sad. Why am I sad? Well, I think that would make me sad. I only have one column, though. Right? I have, lambda equals 1, lambda equals 1. I can't plug in lambda equals 1 again because it would give me the same thing, right? I'm only going to plug it in once. I'm hoping to get 2 eigenvectors out of this. But I didn't. I just got 1 eigenvector. So now I plug in lambda equals 2. I will also get 1 eigenvector. But I'm not going to have 3 eigenvectors. So I can't do the diagonalization here. I'm short. I am short of eigenvectors. What about this one? I changed it a little bit. This is a different matrix. Right, all I did was change one little value here. I turned that one into a 0. Well, let's see what happens. Now I'm going to take this thing. All right, that means that a minus lambda I is 1 minus lambda 0, 3, 0, 1 minus lambda 4, 0, 0, 2 minus lambda. There's my a minus lambda thing. I'm going to plug in lambda equals 1, so when lambda equals 1, this thing reduces to 0, 0, 3, 0, 0, 4, 0, 0, 1. When I row reduce this, well, I'll take that one and turn it into a 1. I'll use it to eliminate the 4. I'll use it to eliminate the last one. And should row reduce to this form. Now I have two free variables. Absolutely. So this tells me my solution is, well, x1 is a free variable, x2 is a free variable, and x3 is 0. So when I write this out parametrically, I have to have the sum of x1 stuff plus the sum of x2 stuff. It's going to look like x1, 0, 0, plus 0x2, 0, which is x1 times 1, 0, 0, plus x2 times 0, 1, 0. And now I'm happy. I have two eigenvectors for this thing. The eigenspace that's associated with lambda equals 1 has two basis vectors. So each of these eigenvectors, remember there's infinitely many eigenvectors, I won't say these are the only two eigenvectors. Any multiple of these and any linear combination of these two is an eigenvector. So the basis for this eigenspace is 2. I'm pretty happy about that. Now I can take these two eigenvectors, pair them up with the one I get from lambda equals 2, and I will have 3 eigenvectors. I can form P. I can do this diagonalization thing. Okay. Now what happens when I only have the one eigenvector up here? There's a big long process for generating a special extended eigenvector. They call it the generalized eigenvector. That's beyond the scope of this class though. So there is stuff we can do to kind of fit in some third vector to do a pseudo-diagonalization. It's called the Jordan form. Once again, that's a little beyond this course. For our class, we're going to need to work with cases where we have enough eigenvectors so we can actually do the diagonalization. All right, any questions about that? Now, of course, we need a way to describe this, right? So you say, well, how do we know if we can diagonalize? Well, if we have repeated eigenvalues and then when we try to plug the eigenvalues in and we don't get enough eigenvectors, see, that's already too long, right? Mathematicians don't like this. So all we have to do is give a bunch of fancy names to this stuff, right, to make it sound complicated. So again, that's what mathematicians do, right? So that's what we're going to do. We're going to say the number of times an eigenvalue is repeated is called its algebraic multiplicity. Algebraic multiplicity. The dimensions of these eigenspace, in other words, the number of basis vectors in the eigenspace, that's called the geometric multiplicity. And now, if we want to say that if A is diagonalizable, we'll say that it's diagonalizable when what is true? Yep, we need the right number of eigenvectors, right? Now we'll have that for sure unless there is repeated, right? And if it's repeated, say I have 2 1s. How many eigenvectors do I need when I plug in lambda equals 1? 2, right? So in other words, when it's the number of times lambda is repeated, I have 2 2s. Its algebraic multiplicity is 2. I need its geometric multiplicity to be 2. So in other words, A is diagonalizable if its algebraic multiplicity is equal to its geometric multiplicity. You see how we try to complicate that thing? It's easy enough to say, okay, yeah, repeated eigenvalues, you need enough eigenvectors. No, that's not good enough. You need to make up a bunch of fancy terms so we can say this nice in one sentence, right? Okay. All right, so it's diagonalizable if the algebraic multiplicity and geometric multiplicity have to match for each lambda. Okay. Once again, this is just our fancy way of saying if you have an eigenvalue repeated 3 times, you need to be able to get 3 eigenvectors from it. Because you need to get enough columns to make your matrix P. All right, you can just tell I have little kids because every time I say something like that, I want to giggle. So I'm saying the word P.
What's the last part of it?
So the algebraic multiplicity
No, the last line.
and the geometric multiplicity have to match
Have to match.
for each lambda. You can see that was match? I can't read that.
No.
Okay. Okay, so why? Why do we want to diagonalize? Couple reasons. Right? One important application is being able to find the powers of A. And the next one we're going to talk about is how we can view diagonalization as really just working with the best basis. We're going to see that the eigenvalue or eigenvectors are really the best basis to represent A with. Now, first we'll look at the powers here. I have A, and I want to take A times X. And then I want to take A times the result. And then I want to take A times the result of that. That's the same thing as taking A raised to some power times that value X. But taking A raised to a power is hard to do. Right? This is not just taking every element of A and raising to a power. It doesn't work like that. We do the multiplication, all the terms kind of get mixed up. So we would really have to multiply A times A 10 times. That takes a lot of computing power. But if we know that this is true, then we can write A times A times A as P times D times P inverse times all that stuff over and over again. So kind of like this. P D P inverse times P D P inverse times P D P inverse dot 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 P D P inverse. But now, because matrix multiplication is associative, I don't need any of these parentheses. And now if I just change the order and do this one first, what do I get here? What's P inverse times P? I. Right, and over here I would have this thing times P D P inverse. Here's I. And so when I just expand all this out, all I get is this thing. And that's nice, because while it's hard for me to take this matrix and multiply it by itself 10 times, it's not hard for me to do this matrix times itself 10 times. Because if I have a diagonal matrix, 2, 1, 0, 0, for instance, times 2, 0, like this, the result is going to be, well, let's see, 2 times 2 here, so 2 squared, right, plus 0, 0, 0, 0, and 1 squared. And that generalizes it. So in this case, if I want to take D raised to the 10th, all I have to do is raise each of those diagonal entries to the 10th power. That's much easier than actually doing this matrix multiplication 10 times. Okay? So it's much, much easier to be able to take a matrix A, find the eigenvalues, find the eigenvectors, form the diagonalization, and then just take this to the 10th power, than actually take this thing to the 10th power. And that happens a lot in real application. We have these things called difference equations, where essentially a system is modeled by repeated applications of A, repeated multiplications. So this is the way we can do this very efficiently. Okay, so raising matrices to powers, very important in modern algorithms. A lot of algorithms we do with computers do repeated multiplications of a matrix, and so the computer will actually use this as well. We use the theory to simplify the calculation so we can do more calculations on bigger systems. And the difference equations are a specific example. We'll get into that a little bit next time. Next time we're also going to finish up by talking about this best basis idea. We want to talk about how eigenvector, this diagonalization, is really in disguise a change of basis. So we're going to look at that, and then we're going to make it a work session. So I'm going to bring in some worksheets for us all to do. There'll be a quiz on 2.8 through what we've currently done. So that's column space, null space, Change of coordinates, all the way up to eigenvectors and eigenvalues. So we'll have a quiz on kind of that whole big window.
So that's 2.8 to 3.2.
2.8, 2.9, 3.1, 3.2, 4.4, 5.1, and 5.2. So everything on the schedule from 2.8 up till today.
Okay.